In the last video, we started talking about solubility equilibria. So we said that insoluble ionic compounds or insoluble salts are actually slightly soluble. So some of those ions do dissociate in aqueous solution. It is an equilibrium reaction, right? It's reversible and it can reach equilibrium. So we could write our equilibrium constant expression. It's defined by an equilibrium constant called our solubility product constant. And then we were calculating our solubility product constant given the solubility of our ionic compound. What we're going to do in this video is we're going to go backwards, right? Given our solubility product constant, we can actually calculate our solubility. And then we're also going to look at some factors that affect solubility. So we can use the solubility product constant to calculate the solubility of the compound. And as usual, the easiest way is to just jump into an example. So we're going to look at iron 3 hydroxide. Again, be sure to review nomenclature if you need to. So iron 3 hydroxide has a solubility product constant of 2.6 times 10 to the negative 39th. So not very soluble at all, right? That's a really, really small number. So we're going to calculate the molar solubility. So just the solubility with molarity as my units of iron 3 hydroxide. So we're not going to expect a very large answer, right? It's not very soluble. If I have 1 liter of solution, I'm not going to have a lot of moles of my compound. So just like we were doing in the last video, we're going to start by writing our equilibrium equation. So this is solid. It is going to dissociate a little bit into iron 3 plus 3 hydroxide ions. I write my expression. I'm going to leave a little bit of space because we are going to make a little table under there. So my solubility product constant, which we can actually write the number if we wanted, since we're given it, 2.6 times 10 to the negative 39th is equal to my concentration of iron 3 plus raised to the first power because there's 1 of them, multiplied by my concentration of hydroxide ions raised to the 3rd power because I have 3 moles, right? Raised to a power equal to its coefficient. And then I don't know what the solubility is, right? That's what we're solving for. We have no idea what it is. So we're going to call that X. Because for every one of these, there's one of these. If iron 3 hydroxide is X, iron 3 plus is also X, right? It's a 1-to-1 relationship. And then I have 3 hydroxide ions. So this is actually going to be 3X, right? For every one of these, there's 3 of these, so 3x. We're then going to take these values and plug those into my expression. So 2.6 times 10 to the negative 39th is going to equal x multiplied by 3x to the 3rd. So just like we were doing in the last video, be really careful. We're multiplying this by 3, right? We're multiplying x by 3 because my concentration, right? My concentration of OH minus is 3 times whatever my concentration of iron 3 hydroxide is, right? Because of this 1 and this 3, my concentration is 3x. then my expression tells me that I have to take that concentration, which is 3x, and raise it to the third power. So you're doing two things, right? We're going to both multiply it by 3, and you're going to raise it to that third power. So the concentration is 3x, and then our expression says we take 3x and we cube it. And then just be careful on your math here. 2.6 times 10 to the negative 39th. Didn't mean to switch colors on you. 2.6 times 10 to the negative 39th is equal to x, right? And then you're squaring both the 3 and the x. So 27x cubed, right? It's not 3x cubed, it's 3x cubed, right? These parentheses. So you need to cube the 3, we get the 27. You also need to cube that x. So I have 27x to the 4th. So again, just be really careful. We need to take x and multiply it by 3 because of this 1 to 3 ratio. And then the expression says you take that 3x and you cube it, and then don't forget to cube that 3x. So you need to cube the 3, 27. You also need to cube that x. So 27x cubed times x is 27x to the 4th. Divide 2.6 times 10 to the negative 39th by 27th, and then take the 4th root of it. And when you do that, let me grab my calculator here and type all that in to see what we get. Hopefully you guys are going to do the same thing. And I got 9.9. I am going to double check this here real quick. 9.9 times 10 to the negative 11th. And I just want to double check here. On my calculator, and maybe your calculator is easy, but doing the 4th root is pretty obnoxious. So I just raise it to the 0.25 power. If you raise it to like 1/4, it's the same as taking the 4th root of it. I think that's easier for me. So if it's easier for you, I would recommend it. And then be careful. I'm not solving for an equilibrium constant. I'm solving for my molar solubility, which means I need to have units. Right? We don't have to show units with equilibrium constants. We do have to show units with pretty much everything else that has units. So because I'm solving for my molarity, essentially, you need to put those units on there. So just be careful on that. So another example for us, and I want you to do this one on your own. So I'm going to write down the problem, and then please hit pause, work through it completely on your own, and then when you're done, come back to check your work. So we're going to calculate the molar and gram solubility of silver carbonate. And our solubility product constant of silver carbonate is 8.1 times 10 to the negative 12th. So both molar solubility, so molarity, and then gram solubility, right? That's going to be grams per liter. So you will do a unit conversion after you solve for your molar solubility. Okay, so please hit pause, go through the problem, and then come back. Alrighty, so hopefully you guys did that. I did write silver carbonate in words instead of the formula on purpose. You may have needed to go back and review, but silver is a fixed charge metal. It has a +1 charge when it forms an ion. Carbonate's one of the polyatomic ions. We've used it already in this chapter, so it could be fresh in your mind. It has a -2 charge. So I'm going to need 2 silver ions for every 1 carbonate. It is solid. And I'm going to get 2 silver plus 1 carbonate ion. I know that I don't know my solubility, so we're going to call it X. I know that this is going to be 2X, right? Because I'm going to have 2 silver for every 1 silver carbonate. And then carbonate is just going to be X because it's a 1-to-1 ratio. So 1 here and a 1 here. I know that my expression, 8.1 times 10 to the negative 12th, is equal to silver ions squared, because I have a coefficient of 2, right, raised to a power equal to its coefficient, multiplied by carbonate ions. So that's going to be equal to 2x squared. Again, make sure you square the 2 and the x, right? It's 2x squared, not 2x squared, multiplied by x. So 4x squared times x gives me 4x cubed. I'm just copying this number down. So I'm going to divide both sides by 4 and then take the cubed root. So grabbing my calculator. And I get 1.3 times 10 to the negative 4th. And then this is my molar solubility, right? X is my solubility that I'm looking for. And because of these brackets, right, we know that it's molar solubility. So we're going to throw a capital M after it. So that's my first part. And then we know to convert between molarity, right? Molar solubility is moles per liter. And grams per liter, I need the molar mass. So let's calculate that real quick. And I'm grabbing my periodic table. So silver, I need to multiply its molar mass by 2 because there's 2 of them, plus my molar mass for carbon, plus the molar mass for oxygen that I multiply by 3 because there's 3 of them. And I get 275.75 grams per mole. And I am just going to double check that real quick. Oops, I did something wrong. I got 9,044 this time. That's not right. Okay, yeah. So taking 1.3 times 10 to the negative 4th moles per liter, right? This time moles are on top. I want moles to cancel. So I'm going to multiply by my molar mass. When I do that, moles will cancel and I'll be left with grams per liter. And I end up with a gram solubility of 0.036 or 0.36 times 10 to the negative 2. And then again, don't forget your units. And factors that affect solubility. And the first one we're going to look at is the common ion effect. So a similar sort of idea as before, we're going to be providing a substance that provides an ion that's in common with one of the ions already present. So our first one, common ion effect. And I'm going to leave a little bit of space because we're going to come up and write a sentence here, but I want us to just kind of think about it first before I tell you the answer. So I'm just going to use magnesium fluoride as our insoluble or slightly soluble ionic compound. It is going to dissociate into magnesium ions plus 2 fluoride ions. And then let's say we're also going to add sodium fluoride. And we know that sodium fluoride is sodium ions and fluoride ions, right? Sodium ions aren't part of this equation, so that's obviously not the common ion part that we're talking about, right? It's the fluoride ions. So we have magnesium fluoride, we add a sodium fluoride solution to it. That gives us fluoride as a common ion. So what is going to happen? Is this going to increase or decrease our solubility? Think about it as Le Chatelier's principal effect, right? Because that's all it is. If I was to add more fluoride, which is what I'm doing, right? By adding sodium fluoride, I'm adding fluoride ions. So I'm adding something that's a product. Which way does it shift? Right? If I add a product to this, which direction does my equilibrium shift? If you guys are saying towards reactants, great job, because it is, right? If we add more products, remember we have to undo what we did, so we need to shift in this direction. And this side, right, the way that I'm shifting is my solid. So we're actually decreasing solubility, right? The more soluble it is, the more ions I have. The less soluble it is, the more solid I have. By adding a common ion, I'm shifting it towards that solid, so my solubility is actually going to decrease. So that's what we want to write here. So the solubility of a slightly soluble ionic compound is decreased in the presence of a common ion. And again, it's just a Le Chatelier's principal effect, right? We're adding fluoride ions that shifts it towards my reactants. My reactants is my solid, so less, right, ions, more solid. My solubility is decreased. Will actually precipitate our solution. We could say it that way also. So we'll precipitate more of the compound from the solution. Right? If I have a saturated solution of magnesium fluoride, I add sodium fluoride to it, we're going to precipitate some of that magnesium fluoride. So we're going to end up with some solid forming in the bottom of our container. I do want to go through a calculation. So I'm just going to erase this temporarily. We're going to calculate the solubility without a common ion, and then we'll add that common ion and calculate our solubility. So using the example that we just had, what is the solubility of magnesium fluoride? And we need its KSP, and it is 7.4 times 10 to the negative 11th. And then what is the solubility of magnesium fluoride in the presence of 0.020 molar sodium fluoride? So 2 parts, A and B. And part A is just what we've been doing, right? We know that our solubility product constant, which is equal to 7.4 times 10 to the negative 11th, is going to be equal to my concentration of magnesium ions raised to the first power multiplied by my concentration of fluoride ions raised to the second power. And then to get those concentrations, I didn't really leave enough room here, but we'll do it on top, right? If this is X, magnesium is also going to be X because it's a 1-to-1 ratio. And then my concentration of fluoride ions is actually going to be 2X, right? Because for every 1 here, right, there's a 1 here, I have 2 fluoride ions. So then plugging those in, I have X for my concentration for magnesium, and then 2x for my concentration for fluoride, and we do need to square that. So then working through the problem, I have 4x cubed. I'm grabbing my calculator. And I get that x is 2.6 times 10 to the negative fourth, and then x is representing my molar solubility, so I'm going to put a capital M for molarity at the end of it. B. And I'm just going to rewrite our equation just so I have some more room here. So the one that we wrote up here, magnesium fluoride forming magnesium ions plus 2 fluoride ions. And then this time our concentration of fluoride is actually going to come from 2 sources. Right? The first one is from the dissociation of magnesium fluoride. So that's the 2x that we had before. Right? If this is x and there's 1 mole of it, this is going to be 2x because I have 2 moles. And then my second source is going to come from our 0.020 molar sodium fluoride solution. Right? Since there's 1 fluoride ion for every 1 sodium fluoride, that number is going to be 0.020 molar. So at equilibrium, right, my concentration of fluoride is actually this plus this. So looking at our expression here, my solubility product constant is still the same value because it's still magnesium fluoride, and we're going to assume the same temperature. My concentration of magnesium is still going to be x, and then my concentration of fluoride this time is going to be the 0.020 molar plus 2x. Right, my 2 sources. And then we still need to square that because we still raise it, right, to a power equal to its coefficient. It's still this expression. It's just that this number is coming from those 2 sources. So 2x from the dissociation of magnesium fluoride, and then my common ion that we're adding. And then because my KSP is small, we can assume that this 2x is negligible compared to the 0.020 molar, which makes our math a lot easier. So we can assume this is negligible. And if you're a big fan of the quadratic equation, by all means, go ahead and do it both ways and kind of compare your answers. So as our KSP is small, which means I can rewrite this one more time to be 7.4 times 10 to the negative 11th. It's going to be equal to x times 0.020. So grabbing my calculator here. I get that my solubility is 3.7 times 10 to the negative 9th molar. And then remember, adding that common ion, we're expecting our solubility to decrease, right? Le Chatelier's principle, adding a product is going to shift my reaction towards reactants. That reactant is my solid. So my solubility, which is what we're solving for, should be smaller, and it is, right? Without the common ion, I had 2.6 times 10 to the negative 4th. With that common ion, 3.7 times 10 to the negative 9th. Our second factor is going to be the pH of the solution. And this effect only occurs if you have a basic ion as part of your equation. So the solubility of an ionic compound increases this time, and we'll look at it here in a minute, with decreasing pH, if the solution contains a compound let's just say contains a basic anion. So the solubility is going to increase this time. With our common ion effect, we actually saw a decrease in solubility. This time we're going to see an increase in solubility as our solution becomes more acidic, right? Decreasing pH, so it's becoming more acidic, if the solution contains a basic anion. And generally it has to be pretty basic. Like the pH of the solution to begin with should be less than about 10.45 for this effect to actually occur. Don't worry about remembering that number. Just do know that it has to be a basic solution, right? I have to have a basic anion as part of it. And the easiest way is to just look at an example. So we'll look at magnesium hydroxide. And we're going to form magnesium ions and 2 hydroxide ions. And we know that hydroxide ions are basic, right? That's our strong base essentially. So what happens is we're going to add acid to it, right? If we want our pH to get smaller, right, decreasing pH, we need to add acid. So as the solution becomes more and more acidic, what we're essentially doing is we're removing this base, right? As H3O plus is added, our hydroxide ions are neutralized, right? We're going to form water, right? It's going to react with the acid to form water. Which is effectively removing it from solution. Right? I no longer have hydroxide ions floating around because those hydroxide ions have reacted with the acid that we added to form water. So what I'm doing is I'm removing a product. So again, just back to Le Chatelier's principle, right? If I was to remove something from this side, I have to shift it towards products to make more of it. Since I'm shifting towards my aqueous ions and away from the solid, I am increasing my solubility. So I have an anion that's basic, we add acid to it, that acid neutralizes that base, which essentially is just removing it from solution. So I'm removing hydroxide ions by reacting it with the acid, shifting towards products, increasing my solubility. I do want to quickly talk about, I had said with a pH less than 10.45, and that's specifically for this example. And I just kind of as a side note want to go through why that number, just because I want us to start thinking about everything that we've learned and how I'm getting that. So my KSP for magnesium hydroxide is 1.2 times 10 to the negative 11th. And if we were to solve for our molar solubility, right, that's going to be equal to the concentration of magnesium, which is going to be X, multiplied by the concentration of hydroxide ions, which is going to be 2X, right, because there's 2 hydroxide ions. And then I need to square that, right, because I need to take the concentration of hydroxide and square it. So solving for X real quick, I'm grabbing my calculator here. I got 1.4 times 10 to the negative 4th molar, which is my molar solubility, right, for magnesium hydroxide. But if we wanted to calculate our concentration of hydroxide ions, right, it's going to be 2 times that number. So 2 times X, right, if I go back up and look, right, my concentration of of hydroxide ions is 2 times X. So 2.8 times 10 to the negative 4th. So if I wanted to calculate the pH of my solution, like that's a question I could ask, right? I'm going to first do the pOH. You could do it the other way by dividing your hydroxide ion concentration into kW, but I do tend to prefer this one. So I'm going to take the negative log of this number. I get 3.55. So the pH of my solution then, I'm just going to subtract the 3.55 from 14, and I get 10.45. So what we're saying is that the pH of this solution is 10.45, right? We just calculated based on my solubility product constant, my concentration of hydroxide ions, and we got a pH of 10.45. So if I'm going to decrease my pH, right, I have to have a pH that's less than 10.45. So that's where that number is coming from. And of course, that's going to vary. If I gave us a different compound that contained a basic anion, the pH that you need to get below is going to depend, right, on the pH of your solution. Number 3 is the formation of complex ions. So complex ion formation. And I'm going to write the effect here, but I will come back and explain what a complex ion is, I promise. So solubility increases, and this is of course the solubility of our slightly soluble ionic compound, if the solution contains a substance that can form a complex ion. And what a complex ion is, it's a metal cation bonded to one or more molecules or ions. So an example, if I was to take silver ion, so silver with a +1 charge, I can actually bond it to 2 ammonium molecules. Since silver has a +1 charge and ammonium doesn't have a charge, this entire thing has a +1 charge. So it would be considered a complex ion, right? I have a metal ion bonded to 1 or more molecules. Because it has a net charge, it is a molecule. Sorry, it is an ion. Sorry, misspoke there. And I don't necessarily expect you to be able to look at a reaction and say, oh yeah, well that obviously can form a complex ion. But I do expect you to be able to know what happens if I tell you that it can form a complex ion. So an actual example here, silver chloride. Using our solubility rules, it is insoluble, though we do know that it's actually slightly soluble. And this one's really, really slightly soluble. Like in water, it's essentially insoluble. But in ammonia solution, my solubility does increase. And the reason for that is ammonia forms that complex ion with silver. So basically, it's almost 100% insoluble. It is still slightly soluble, so it's not 100%, but it's just really not very soluble at all. In ammonia solution, it actually is still not a lot, but it is soluble. We can actually form a solution with it. And again, what's happening is the silver ions, right? I'm taking the silver from here. Because it's in an ammonia solution, I can react that with ammonia, 2 of them. And we can form that complex ion. And then again, that entire thing has a +1 charge. You didn't really need these double brackets up here. I just did it for effect, right? To show that the entire thing has the plus charge. So what we're doing, it's a Le Chatelier's principle deal again, is we're removing this from solution, right? Just like we did with our basic one before, right? I had this, I added acid to it. That acid neutralized that base, right? I don't have hydroxide floating around anymore. I have water. So I remove this, shifting my equilibrium in this direction. It's really the same effect, but just a different reason for it, right? I don't have silver floating around anymore. I can't go back in this direction because what I'm essentially doing is removing this from solution by reacting it with ammonia. So because silver is tied up in this complex ion, right, I'm really removing a product, shifting my equilibrium towards products, right, away from my solid, towards my aqueous ions, increasing my solubility. Right, so essentially, or effectively, removes silver from solution, shifting the original equilibrium towards products, increasing my solubility.